Hello everyone and welcome to Looking for Pythagoras 4.4. Our learning target in this section is I will compare rational and irrational numbers. Our aces for this, just three problems here, 22, 23, and 41. As we look at 4.4, it says getting real, but what we're going after is irrational numbers. What you'll find out later is that whole set of rational and irrational numbers is called real numbers. But it talks to us about how we found in problem 4.2 a decimal with a pattern that went 10, 11, 12, 13, 14, 15, 16. And that's an example of a decimal that never repeats and never terminates. This is another example here. And it says, why does this pattern go on forever without repeating? Well, it's going to keep growing. There's going to be 5, there's going to be a 1, and then 5 2's this next time, and we never get to the end of the answer. It just keeps going around and around and further and further and further, and will go on for infinity. All right? So a big thing to take out of this is you can never represent a non-repeating, non-terminating decimal as a fraction or as a rational number. Gives you some examples here. I encourage you to pause this and read through it yourself. And then it talks about how is this decimal up here, okay? How is this kind of decimal the same as or different from the repeating decimal of 0.6666 and a repeating decimal of 0.121212, or the terminating decimal of 1.414213562? Okay, these are all three of these are either terminating or repeating. Okay, and this is non-terminating and non-repeating. So that's how they're different. You might want to pause it and see how you can find out how they might be the same. Take a little look at that. Now, as we go on here, it tells us the numbers with decimal representations that are non-terminating, non-repeating are called irrational numbers. So put that in your vocabulary bank of irrational numbers. And you've dealt with irrational numbers before earlier in this unit, and even prior to that. Pi, our good friend pi, is irrational. It starts off as 3.14, as most of you know, and then it continues on 159.265, and there is no end to the decimal for pi. It goes on forever and ever. At least so far, nobody's been able to find an end to it, and it appears that it will always be irrational. One you've used earlier in this book is the square root of 2. It's also irrational. We've estimated it to be 1.4 or 1, and then we might continue on, but it will never end or terminate as well, and it will also never repeat. So the square root of 2 is an irrational number, as are the square root of 3, square root of 5, square root of 11. Now, write this part down, okay? Pause it, write this part down. In fact, the square root of n, meaning any number we put in there, the square root of n is an irrational number for any whole number, that means non-decimal number, value of n that is not a square number. Okay, square numbers are numbers like 1, because 1 times 1 is 1, or 4, 2 times 2 is 4, 9, 3 times 3 is 9, so on and so forth, and I've listed quite a few of them here. All right, all of these numbers are whole numbers that are square numbers, so they are rational. Okay, all the other numbers in between these are irrational. Okay, or the square root, if they were in a square root, they would be irrational. Okay, square root of 3 is irrational, square root of 8 is irrational, square root of 26 irrational, those sorts of things. Okay, so take a look at that. And it says, are the following numbers rational or irrational? Well, you can go back and take a look here where it talks about the whole number value of n that is not a square number. So are these square numbers? Which ones of these are, which are not? Can you give another number that has a rational square root? Well, I gave you a bunch of examples on the previous slide. And can you give another number that does not have a rational square root? Well, if you go back to our definition, there's a lot of those available that you should be able to list as well. Now, the set of irrational and rational numbers is called the set of real numbers. Okay, pause, put that in your vocabulary bank as well. Now, an interesting thing tells us here, amazing fact, but there's an infinite or limitless number of irrational numbers between any two fractions. So like between 1/4 and 1/2, there's an infinite number of irrational numbers in that, and every irrational set of irrational numbers you find, you're going to have another infinite set of irrational numbers in between those two, and it will go on and on forever. So for the problems here in 4.4, we're just going to do parts C and D, okay? The diagram shows a square drawn on the hypotenuse of a right triangle. Find the length of the sides of the square and the area of the square. Well, I did this one for you to give you that idea. Again, we've had some practice here with knowing the length of one leg and the length of another leg. We apply the Pythagorean theorem. So we have a squared plus b squared equals c squared. Okay, and c squared would be 5. So the side length, we need to take the square root of that. That makes this a square root of 5. Well, if you square the square root of 5, you're going to get an area of 5. So knowing all of that, take a look at number 2 where it says, Ty says that this proves that the square root of 5 times the square root of 5 equals 5. Do you agree? And be able to explain to me why you do or do not agree. And then in part D here, all we're doing is telling whether each number is rational or irrational and explain your reasoning. If you get a little confused, pause the video, go back to a couple of slides ago with what we talked about right here, okay? And that should help you determine whether these numbers are rational or irrational. So you just want to put an I or an R for each of these, I for irrational and R for rational. So that's it for the problems, and then again we just have the 3 ACES problems, 22, 23, and 41. Hope this was helpful, and let me know what questions you have, and look forward to seeing you in class.